All right, I want to try to explain this convergence theorem specifically in the context of Q-learning. It's intended to be general and apply to lots of algorithms of this form, but mostly we want to use it to show that Q-learning converges. So let me express Q-learning as an update rule in the form of this kind of weird BT operator notation that was used in the theorem. Okay, so BT is the operator that we're going to use to update the Q function on the T time step. And so given that we know that we're on the T time step, we know that we're in some state st minus 1, took some action at minus 1, ended up in some new state st, having received reward rt. All right, so what I'd like to kind of argue is that this strange definition of the operator BTQ is exactly the Q-learning update. So let me try to argue that. So this looks a lot like the Q-learning update, right? That says that we're going to take the Q function at SA and we're going to move it a little bit towards the immediate reward plus the discounted value of the next state, that much toward where, with the old, away from where that old Q value was. So the only thing that's different between the Q-learning update and this is that we've separated out two different Q functions, this W thing and this Q thing. Q is using to play the role of essentially the Q function in the state action pair that we just left, and W is playing the role of giving us an estimate of what the Q value is at the state that we just arrived in. And in regular Q-learning, those are the same, but we're now separating them out because the theorem is going to find that easier to swallow.
Okay.
All right, so you buy the fact that this is Q-learning, just in a slightly different notation?
Well, it certainly is if W and Q are the same, which is what you just said.
Yes, certainly the case now that W and Q are different. But when you're saying it is Q-learning when W and Q are the same?
Isn't that what you said?
Yes.
Okay, so yes, that's what I'm saying.
Great. All right, so now what we want to argue is that this definition of the update rule causes the things that we needed to be true for the theorem to be true. All right, so let's start with condition 1. Why is this true for the learning rule defined this way?
But is that a question, or you? That's rhetorical, right?
It was intended to it was intended to actually be a question. So let's look at what needs to be true of this learning rule. What needs to be true is that if we have essentially if we did this update in the form of knowing what Q star was and use it as our one-step look ahead here, then what do we want to be true? What we want to be true is that if you give me any two value functions, they're going to get no farther apart. In fact, they're going to get closer together if the learning rate, if we're actually updating that particular state action pair and the learning rate is non-zero, they should be getting closer together. So why is that the case? Why is it the case that if we do this update at a state action pair, doing our look ahead with Q star, that everything is sort of moving towards one particular answer? It's moving towards a particular answer. Do you know what it is?
Q star.
It is moving towards Q star, but in particular, it's trying to compute the expected value of this one-step look ahead, where the expectation is taken over at all possible values of ST. So it's essentially doing the averaging part of the Bellman equation, and the reason that works is because, well, that's sort of how things converge if you let learning rates converge, and we've talked about that in previous lessons. So all this rule is saying is that if we knew where we were going, we could use this update rule to average out all the stochasticity that we get on different trials, taking a step from a state and ending up in a different state because of the stochasticity of the transition function. So that's all this is saying, is that we can smooth out the stochasticity in the transition function using the rule that we're worrying about.
Okay, that makes sense.